is Tricia Dunlevy. For my fifth lab, I observed the motion of a ball of yarn, as well as a plastic bag. The ball of yarn was a fast-moving object, the plastic bag was a slow-moving object. And I found that the drag force acting on the slow-moving object is significantly greater than the drag force acting on the fast-moving object, which is minimal. I chose the start time of my ball to be right after it was dropped. You can see that it has left my hand at this point. The choice of origin, I chose to be the center of the ball in the first frame, and then I chose the axis to be along the path of motion of the ball, as determined by the end point where I chose to end my video. The length scale is determined by this calibration stick, where I measured the width of the ball to be 0.102 meters. The time between frames is about 1/30th of a second, and the total time of the clip is about 0.534 seconds, going to when I chose to end it before the ball hit the ground. So here you can see my code for the computer model of this object. I found the mass by weighing the ball to get a mass of 0.0752 kilograms, and then I set the initial position equal to the position that I got from the tracker data, and then I set the initial velocity of the ball equal to 0 because it was being dropped from rest. And I set the time step as delta t equals 0.01 because it was very small compared to the time interval of 0.534 seconds. And then for this part of my code, you can see that I set the time the end time equal to 0.534 because that was the time I got from my tracker video. And then I set the force of gravity equal to the opposite of the ball's mass times gravity. And in this model, I chose to neglect drag, so I set this equal to 0, with the force net being force gravity added to the drag force. And then I used Newton's second law to get update the position, or update the velocity of the ball, and then also updated the position by by adding to the initial position the velocity times the change in time. When I ran the computer model, you can see that the ball was moving in the negative y direction, and the motion appeared parabolic due to the acceleration due to gravity. When I plotted the data together, you can see that the match is pretty good, but not excellent. This is probably due to existence of other forces, or perhaps filming error, and not holding the camera completely still. Then to create the model for the fast object using the drag force, I kept the initial conditions the same and kept the force of gravity the same, but added a drag force equal to a proportionality constant, and the opposite of a proportionality constant times the ball's velocity. And I manipulated the proportionality constant to get the graph to match the graph of my motion, experimental motion, but I found that I kept decreasing b to get it to match, and as b got smaller and smaller, the graph didn't change. It changed by only minuscule amounts, so I ended up with a b of 0.0001. In this model, you can see that the ball also moved in the negative y direction, but the motion started out approximately parabolic and then became approximately linear as these forces began to balance each other out. So when I plotted the data together, you can see that they have approximately the same relationship as the relationship between the motion and gravity, and this is probably because the effect of drag force is minimal on the fast-moving object. To analyze the motion of dropping the plastic bag, I chose the origin to be the center of the bag at the instant after the bag is first dropped, which I chose as my start time. And then I chose the axis to be aligned along the path of the bag, using the end point of the bag to find it. And I set the center of mass as the center of the bag. And then for the length scale, I used a calibration stick based on the width of an exit sign, because the width of a bag is hard to determine at any given instant because it's constantly changing shape. And I found that the width of an exit sign is 0.324 meters. The time between frames is about 1/30th of a second, and the total time of the clip is about 1.335 seconds. And I chose the end time to be before the bag touches the ground, so you can see that it hasn't yet touched the ground in this. To set the initial conditions of the bag, I found the mass of a typical plastic bag to be about 0.005 kilograms, and then I got the initial position from the tracker data of the first frame, and set the initial velocity equal to 0 because the bag is dropped from rest. And I chose delta t to be 0.01 because it's sufficiently small compared to the time interval of 1.335 seconds. To create the model of the bag with only gravity, I set it up exactly the same as the other model, with the force of gravity equal to the negative ball's mass times gravity, and then I set the force of drag equal to 0. When I ran this model, you can see that the ball again moved in the bag again moved in a negative y direction in approximately parabolic motion. When I plotted these data, the experimental data and the model data on the same graph, you can see that the relationship is very different between the two. And this is due to the fact that there are other forces acting on the bag besides just gravity. So to make a model of the bag with gravity and drag acting on it, I added in the force of drag to be the negative b, the constant in proportionality, times the ball's velocity. And I manipulated b to get the data to match my graph, so I ended up with a b of 0.05. When I ran this model, you can see that the the motion began approximately parabolic, but then remained basically linear for most of the motion because the drag force and the gravitational force equaled out. And then when I plotted the experimental motion and the model's motion together on the same graph, you can see that there's a very good relationship between the two. So it is quite likely that the slow object moves slower because of the drag force acting on it. In question, I compared the graphs given by the velocity versus time graphs given by the models with gravity and the model with gravity and drag. So for the model with gravity, you can see that the velocity does not reach terminal velocity, and this is because the force acting is constant, so the net force will never equal zero because of the force of gravity. But in the case of the gravity and drag model, the velocity does reach a terminal velocity at about 0.6 seconds. And we can assume that this is because the force net at this point equals zero. So the gravitational and drag forces are balancing each other out.